I'm going to introduce myself. I'm Christos Rantsoudis. I'm currently doing my postdoc in Simon Fraser University under the supervision of James Delgrande. In this talk, I'm going to present our work on a new preference-based approach for NMR, and in particular, a first-order framework to represent, interpret, as well as infer default information. The title of the paper says exactly this. It's a preference-based approach for representing defaults in first-order logic, and I'm gonna start with some motivation. So we were originally interested in examining non-monotonic reasoning in the context of full first-order logic, and once we achieved that, examine possible applications of such a framework at specific fragments of first-order logic, and more specifically, decidable expressive fragments like the family of description logics. The intuition is that non-monotonic phenomena are arguably much more general than what appear in the standard examples. And as we will see later, a first-order framework seems more adequate for dealing with them. So from the knowledge representation standpoint, we first want to look at ways to adequately represent default information, and from the NMR standpoint, how to satisfyingly infer external information by default. As we will see, the differentiating factor in our approach will be our association of normality with respect to specific attributes, something that we think produces a more nuanced investigation of defaults. We begin with some basic examples from the literature in order to showcase this point. In the usual birds fly example, the usual interpretation is quite simply that a normal bird flies. Our interpretation, and what we believe makes most sense, would be to say that with respect to the property of flying, a normal bird flies. When we say that penguins don't fly, again, instead of just expressing that a normal penguin does not fly, we associate this with the property of flying. The difference then is when we look at another attribute and interpret the expression birds build nests with respect to the property of nest building, as opposed to the usual interpretation of looking at normal birds in general. The goal then would be to create a framework where an individual is not simply normal or abnormal, but rather is normal with respect to a particular attribute or property like the ones we just saw. As well, we would like for this to generalize to arbitrary relations. And the result of this would be the following. Whereas in the usual interpretation, a bird abnormal with respect to flying is abnormal in general, and so nothing can be concluded for other attributes like nest building. In our interpretation, a bird abnormal with respect to flying may be normal with respect to some other attribute. So for example, penguins can be inferred to build nests even though they do not fly. Some more results that we would like to obtain are three very important principles of defeasibility that most established approaches from the literature seem to not really capture. The first one is inheritance, where individuals will inherit all typical properties of the classes to which they belong, except for those we know are exceptional. We just witnessed this in the previous slide, where we said that penguins can be inferred to build nests, although they do not fly. Next is specificity, where properties are ascribed on the basis of most specific applicable information. For example, if we know that birds fly but penguins don't, then a specific penguin, being also a bird, will be inferred to indeed not fly, since being a penguin is more specific than being a bird. And finally, irrelevance, where default inference is not affected by irrelevant information, meaning, for example, that if birds fly, then a yellow bird will also be concluded to fly, since being yellow is irrelevant with respect to flight. Yeah. So we take a preference-based approach, which is quite common in NMR. Such approaches employ preference orders over models or possible worlds, where worlds or models are ordered with respect to their relative normality. Something holds normally then simply when it holds in the most preferred such models or possible worlds. Conditional logic, circumscription are some of the most prominent examples of such an approach. So what's the difference in our approach? First of all, since we employ a first order setting, preferences are expressed within the models rather than between them. This means that for each n-ary relation, we associate an ordering, and more specifically, a total preorder over n tuples of individuals. This then will give the relative normality of such a tuple of individuals with respect to the associated relation. How will we express defaults in such an approach? We simply make assertions regarding sets of individuals that are minimal in ordering that corresponds to some property or relation. So we see that it's, we create a much more informed way of minimality. The language we employ is based on first order logic, enhanced with so-called predicate formic constructs. These constructs, as their name suggests, are treated as predicates and have the following form: P of y, comma, phi of y, for some terms t. In this expression, P is any predicate symbol, phi is a well-formed formula, and y is a tuple of variables effectively bound within this expression. What is the meaning of such a predicate forming construct? It denotes those individuals that satisfy phi and are minimal in the ordering corresponding to P. As for the models, as we previously stated, they are enhanced with preference orderings, well-founded total preorders, one for each relation in the domain. Some examples of this new logic then are the following. Birds fly is expressed as all the elements that satisfy bird and are minimal in the ordering associated with fly, which means the minimal birds with respect to the property of flight, indeed fly. For penguins don't fly, it's similar. This predicate forming construct gives the minimal penguins of the fly ordering, which are then denoted to not fly. For an example of hierarchy, take parents like their children. We then say that for all the minimal pairs according to the likes ordering, such that y1 is parent of y2, that the first likes the second. Similarly, for children like their parents, we simply reverse y1 and y2 and write that for all the minimal pairs according to likes ordering, such that y2 is a parent of y1, the first likes the second. So these new well-formed formulas, as we see, seem a bit more complex than standard notation, but are so much more informative in the in what normality we would like to achieve. For some results that we obtain in the paper, first, a characterization theorem in which we extend the sets of predicate symbols with some new predicates and use them to express the various orderings instead of them being directly embedded into the models. Using the above, each predicate forming construct can be translated into a standard first order formula and effectively reduce our new logic to standard first order logic when evaluating formulas and more specifically defaults. Some further results are properties like reasoning about defaults, which can be done directly within our framework, as well as showing that compared to the well-known KLM systems, our approach is more expressive since any proof with respect to the former can be transformed into a proof in ours. Moving on to default inference now, we first note that the logic by itself up to now is monotonic, able to express default information the way we envisioned. Next, in order to infer default information, we employ a semantic approach, and in a similar manner to those of other preferential logics, we define preferences between the models. A statement then follows by default, if and only if it is entailed in all minimal such models. Again, what is new in our approach is that we have multiple orderings inside our models, and so we can define more nuanced preferences between the models. As a result, the three principles we highlighted earlier are indeed handled appropriately in our approach. We now go back to our initial interest in applying this framework to decidable first order logic fragments and specifically description logics. Since most of the established approaches to non-monotonic reasoning have been adapted for the DL setting, our immediate goal is to extend our approach to this setting as well. This, of course, would amount to enhancing the domain of interpretations with preference ordering, similar to the full first order case, but most importantly, extend the syntax in such a way that the structure will invoke the use of the predicate forming constructs. What we mean by that is that the current framework would be used as a basis for specific DL expressions to make use of. This would give a greater expressiveness than extant approaches, since normality would be given with respect to specific concepts or roles. And we believe known problems from the literature would eventually be overcome, like the problems related to inheritance. For example, going back to the birds fly expression, whereas in a standard description logic, it would be simply expressed by bird subsumed by fly. There are various ways in the literature to represent through defeasible DLs, defeasible subsumption, the expression all typical birds fly. Our goal is to create a new DL expression that, whatever its syntax, will invoke the use of this predicate forming construct and will eventually be semantically equivalent to this whole expression. Let us also note that our approach in its current form is indeed much more expressive, not only from description logics, but most other approaches in general. Consider the ambiguous statement undergraduate students attend undergraduate courses. In the paper, we have at least 4 different interpretations of this example, which we are able to successfully express. Normally, the things undergraduate students attend are undergraduate courses. Normal undergraduate students attend only undergraduate courses or some undergraduate course, or simply normally undergraduate students attend undergraduate courses. As I mentioned, other NMR approaches seem unable to do the same, and thus, at least from a representational standpoint, we think our framework contains serious advantages. And in our opinion, being able to use this as a basis and obtain such interpretations in description logic would be highly beneficial. More advantages, apart from representational, from applying our approach in description logics would be that the KLM postulates most people would like to hold would indeed follow, as well as the defeasible principles you highlighted, since they mostly depend on the semantics. Uh, Finally, let me say that the full first order setting of our framework will always be more expressive than any DL fragment, since there are examples like this one, elephants like their keepers, that are not expressible in description logics. Again, whereas other first order logic-based approaches we have tried to express them, we believe we obtain a more informed representation, since we do not just say for all minimal pairs such that x1 is an elephant, x2 is a keeper, x1 likes x2 like Brafman does, but do so with respect to the likes relation and likes ordering. For future work, then I simply mentioned that next steps comprise quantifying into a predicate forming construct and thus obtaining expressions like each elephant normally likes its keeper, which is somewhat different from the previous. We could also encode nested default assertions, like professors that normally give good lectures are normally liked by their students. Another step would be to allow for complex expression inside a predicate forming construct, and thus make things even more expressive, but also more complex. In presenting default inference, we have only bothered with a semantic approach. A syntactic one, of course, is also of high interest, especially if shown to correspond to the semantic well-behaved one. And finally, extend the approach to description logics as already discussed. And here are some conclusions about the approach. I'll just leave it here, and thank you for listening to me and attending this presentation.